Hey, folks, we're going to talk about the next unit on static equilibrium, but we're actually going to start with a related topic, and that's center of mass. So we're going to be looking at objects that are in equilibrium, and we're going to need to know where their center of mass is. Now, I'll start with the equation for center of mass. We've talked about that before, and I'll rewrite it for you in a second here. But that's also equal to the center of gravity. Okay. Now, those two, for all intents and purposes, are going to be the same location. The only time that I can think of when they wouldn't be the same is if you were in a non-uniform gravitational field, meaning, like, let's say you have a board and the acceleration of gravity at the left side of the board is significantly more than the right side of the board. Well, then these two x's wouldn't be the same. But otherwise, they're going to be the same. So for stuff that we're going to do here on Earth, these two positions will be the same. So the equation is, if you remember, sum of the mx's over sum of the m's. Okay, if you're looking in the x direction, you would do the same thing in the y and z direction if you had a 2 or 3-dimensional object. So my only example here is we've already done this before, but this is kind of like a review. But I do want to do one example. So let's say you have a merry-go-round. Okay, so it's a big metal uh, disc or cylinder. And then let's say it's got a radius r and its mass is big M. All right. At least it was big M until you cut a hole in it like this. Now let's say that hole, the edge of that hole is tangent with the edge of the merry-go-round. The hole has a radius little r. Okay. And what we're going to calculate now is where is the center of mass. So before you cut the hole out, the center of mass was the dead center of the merry-go-round. Well, now where's the center of mass going to be? Well, hopefully you'll recognize that if I take material away from the bottom, the center of mass will shift upwards. So it'll be somewhere up here. Okay. The question is where? Okay. So I'm going to throw some numbers at you here. Let's say the big radius is 3 units and the small radius is 1. How many units will the center of mass shift from the center of the merry-go-round? Okay. Well, the first thing we're going to do is, I didn't actually give you masses, but we do know that mass is proportional to area. So instead of the sum of the mx's over the sum of the m's, I'm going to do the sum of the ax's over the sum of the a's. And it's going to give me the same result, okay, assuming the merry-go-round is a uniform material, which it is. So I am going to call the center 0 position, and we're going to measure everything from there, okay? So the xcm would be the sum of the mx's. Well, you have the merry-go-round, which has a mass big M, and its center of mass is at 0. And then how do you deal with the hole? Okay, well, if you were adding a piece of metal there, you would say plus the mass of that metal times where its center of mass is. But here we're subtracting material, so you say minus, and I'll call that little m, okay, whatever that mass is. And where is its center? Okay, well, its center is, and we're going to go ahead and go this way positive. So by the way, when we get our center of mass, it'll be a negative number. So its center is, well, this is big R, and then this is little r. So this distance here would be big R minus little r, okay? All over, now again, I went with down positive there. If you go with up positive, this would be a positive, this would be a negative, but you would make this whole thing negative too. So you would have another negative in there, but we're not going to worry about that. And then divided by the mass of the merry-go-round, and then minus the mass of the hole, okay, that we've taken away. Okay, now, as we just mentioned a moment ago, mass is proportional to area, and the area of the circle is pi r squared. Okay, so mass is proportional to r squared. So basically, everywhere I see an m, I'm going to put an r squared instead. So xcm is equal to the mass, the big mass, which is big R squared, but then it's times 0, so it doesn't matter, minus the little mass, which is little r squared, times big R minus little r, over big R squared minus little r squared, okay? And then we have numbers for all these. I gave you big R is 3 and little r is 1. So this would be 0 minus 1 squared times 3 minus 1 all over 3 squared minus 1 squared, which would be negative 2 over 8, which would be negative a quarter unit. Okay. Now again, the negative, we said down was positive, so the negative means that this distance here is a quarter of a unit, whatever that unit is. Okay, so that's center of mass. For most of the problems we're going to do, we're not going to have to do all that to find center of mass, but this is just a review of how to figure it out. And I figured I'd throw a twist in there and to actually take mass away. So hope that was helpful, and thank you very much.